Hi everyone. Today I will present the paper titled FedFast Going Beyond Average for Faster Training of Federated Recommender Systems. It was published on KDD 2020. As we all know that recommender systems are widely adopted as tools that can predict the extent to which a user would like things such as food, movies, news articles, and even books. So the starting point of this work is to find the faster ways to train recommender systems in a federated learning setting. But with recent concern about user privacy and government regulations, there is a growing trend to implement and deploy recommender systems in a decentralized way. And one popular method is federated learning. In the standard federated learning setup, which is FedAverage, the way it works is that a global model is hosted on the server and it will randomly choose users who will contribute to training the global model. And the server then send the parameters of the global model to the selected users. And then the user will use their local data to train the local model and send the local model back to the server. And the server will aggregate the model and since we are talking about the recommenders, it's safe to think of the users as users' devices such as phones, laptops. Now, federated learning tends to work well with different models, but there are still some practical issues that could affect how it is used to train recommender systems. The first issue is that federated learning relies on the creation of a representative at a central server. But since the model is trained only by a sampled subset of users, it is possible that some users will end up waiting a long time before they receive a model that can give them useful recommendations. The second issue is that the user sampling component of the FedAverage does not fully exploit user similarities, but this is often done in the field of recommender systems. And the third issue is that model aggregation component use a simple averaging scheme that can degrade the learned user representations. So as the issues mentioned before, all of the issues can be linked to the sampling and the model aggregation component. And this work will also focus on improving these two components. So they proposed FedFast. What it does is to enhance the federated learning algorithm by introducing a smart way to sample users and a better way to aggregate local models. It is designed to work with recommender models that are implemented as neural network that can learn user and item representations using embedding layers. Before we talk about the proposed algorithm, let's first have a look at the recommender problem. So let M and N denote the number of users and items. We can define the user-item interaction matrix Y from users' implicit feedback as this. Here, a value of 1 for Y indicates that there is an interaction between user and item, but it does not mean the user actually likes the item. And these are the observed entries. It can reflect users' interest on the items. Similarly, a value of 0 does not mean that the user does not like the item. And these unobserved entries can be just missing data. And there is a natural scarcity of negative feedback. So the recommendation problem with implicit feedback is formulated as the problem of estimating the scores of unobserved entries in Y, which are used for ranking the items. So formally speaking, we calculate using these equations. Y is the predicted score for interaction between user and item. And the interaction function F maps the model parameters to the predicted scores. And metric factorization is the traditional way to solve this problem. MF associate each user and item with a real valued vector of latent features. P and Q are the latent vector of user and the item. And it estimates an interaction Y as the inner product of P and Q.
Tongnian, here I have a question. What's the value of Y here? It's between either 0 or 1?
I think it's between 0 and 1.
Yeah, I thought this is more like the rating, right? The rating, or it's either you can view it as a real value, a real number between 0 and 1. But it looks like it is you define the YUI. Looks like this is more like a binary. What happened? I saw that it's more like it should be what kind of rating I give to this item, right? It's not like whether I rate this item or not.
Yes.
So what happened here? I mean, is just a typo, or is something that we missed here?
Do you mean this one?
Yeah. Are those two are the same thing? I mean, the YUI and this Y, are they the same range, on the same range?
This Y is the predicted score. And this score can be used to rank the items. But this one,
I believe Y hat is a real number between 0 and 1, right?
Yeah.
It's not a binary one.
Yeah.
YUI is kind of like a definition. It's binary one, either 1 or 0.
Yeah, I think so.
But are they? I mean, are they trying to predict what kind of rating are you going to give to this item, or they just want to predict whether you will recommend this item to this user or not? So is your prediction binary, or is just not just a binary? Actually, you want to predict that ratings there.
predict the rating.
So the rating, right? If the rating should be between 0 and 1, right?
Yeah.
And then, I mean, if you say the so basically, I don't know what kind of data do you have. For example, if you are talking about data, the data is that this is the user, this is the item, then the user I for item 1, they will give them, for example, 0.5 in terms of rating, or they just give them 1 or 0. That's what I'm asking.
The data should be just the 1 or 0, but the output, the predicted score should not just be 1 or 0.
Okay. So this is more like a binary classification, not binary classification. Okay. So it's from this paper, right? From this one, right? The reference on the bottom, right?
Yeah.
Okay. Yeah, let me see. Okay, thanks.
So the core requirement of their proposed system is that the recommendation model is implemented as a neural network that can predict user preferences from the user and item embedding seat length. And they will evaluate their system using the general metric factorization model. And GMF simply learns embeddings from every user and item, and then use 1 or more prediction layers to estimate a user's preferences for an item. For GMF model, P is the user latent vector and Q is the item latent vector, and they calculate the element-wise product of these 2 vectors. And finally, they can exactly regard the matrix factorization. And GMF can be easily generalized and extended to more complicated models, but more complicated models is likely to provide more accurate prediction. It will have more parameters to learn. So in their study, they just use the basic GMF model. As for the proposed system, there are 2 important new contributions. First, they developed a sampling method to provide the best data for training by choosing the most informative users. And at the second, they propose an aggregation method to speed up the global model training. This is the whole algorithm. They will train the GMF model over a number of rounds, such that at each round, a different subset of M users is selected using their proposed sampling method to concurrently train local models using their local data. And during the local training, which is the client update, each user makes at least 1 iteration of their training data to independently improve the model and returns the updated parameters WK and the number of training samples they used, which is NK. And finally, at the end of each round, the server will aggregate the model using their proposed aggregation method. So their sampling component is a cluster-based sampling strategy. In other words, they explore the user similarities to ensure that the users are selected to train the recommendation model will have sufficiently diverse preferences. And this makes sense because it would be redundant to have similar users train the same model at the same time, since their contributions will likely be similar. So what their sampling method does is to group similar users into clusters based on their profile similarities, and then choose equal number of users from different clusters. And so the sampled users will be the representative of the clusters they've been chosen from. And each group can benefit from the training experience of their peers that participate in the training process. They use k-means algorithms for clustering, and after sampling in each round, in the subsequent round, this sampling method will return a new partition of users, while the clustering is carried out again over the set of user embeddings to ensure that the clusters consist of users whose user embeddings are similar.
Tony, I have a quick question here. Could you go to the previous one? So what do you mean by metadata? So do we need to provide a metadata beforehand for any kind of federal learning process, for this federal learning process?
Sorry, could you say it again? I didn't hear it clearly.
Yeah, what do you mean by the metadata?
This one.
Yes.
Is the it is the is the summary of the statistic get from the users' profiles.
It's like a user's data distribution, or what kind of statistics? Just because original file learning, we cannot disclose the user data information. So, but obviously here, if you want to group users based on certain kind of metadata, this metadata should be known either by the server or some, users, they exchange this metadata information, right? So I think my question is several fold. First of all, is the metadata privacy sensitive or not? The second is who is going to take the action of this grouping things?
I think they will first get the user representations by doing some statistic calculation of their user profiles. So the original user profile will not be so the privacy can be cannot. So basically, it does not reveal the user's profile because they calculate it using some method.
Is some statistics, like
Yeah.
data distribution?
Yeah, I think it is.
Okay.
I mean, in the paper, have they defined what are the mental data here?
They just mentioned they first get the user representation using some statistic method.
So you mean the metadata is the user's representation?
Yeah.
Oh, so this step, the group user based on metadata, you actually, this is done only once, right? I mean, you are not updated or
Yeah, this
update,
one not updated later.
but this one you are updated here, right? Now you are updated here. So based on this one, well, it's more like initialization. You are group user based on different based on metadata, and later after you aggregate them, you are going to group the user again, right?
Later, it will group based on the embeddings they learned.
Embeddings they learned. So how can you? How can the server load the embedding of a user in this protocol? Because you already send the model back to the server, right? So how can the server load the user embedding? User embedding is not the, so the model is not the user embedding, right?
So first of all, we need to know what is the user embedding. Based on the slides, I saw the learning embeddings is like the match relationship between the user and the items. But I don't know, how do they define the learned embeddings? What is the embedding talk about here?
The embeddings, the user embeddings are and the item embeddings, and the user embeddings, I think, are the it represents the user's information, and the item embeddings are the items that the user that related to that user.
So what is the difference between the is the user embedding also the model? Is it a part of the model or is it independent thing?
I think I can first introduce this, and then we can have a
Oh, okay. Oh, so you have slides about how to aggregate model here, right?
Yeah.
Okay. Then we can go. We can just wait until you explain that. Okay, that's fine.
The aggregation component is a 5-stage process that is invoked after each training round. First, all non-embedding layers of all the local trained models are combined using a weighted average method, as is used in the federated average. The second step combines item embeddings that have been updated in the local trained models. The WK here is the parameter learned by each user who partake in the model training process in each particular round. And W0 is the aggregated value from the previous round. So we calculate the difference between these two values, which is the Q here. And each item embedding component I, for each item embedding component I, the aggregated parameters Wi is formed as a weighted average of the Wk, which is the parameter learned by the participating users. And the contribution of the participating users is proportional to the difference between the Wk and the W0, which is Q. And note that each participating user K only contributes to those components IK here, which is updated during this specific round. So, and finally, this is all the process of updating item embeddings.
Well, this is item embedding, right?
Yeah.
Even for the item embedding, how do you S, what is S? S is the user.
S is the sampled users.
Okay. And then for each user, you will do what is I?
I is the item embeddings.
So it's the item set.
Yeah.
And what is WK?
WK is the parameters learned by the participating users in the.
But the item, but why the this model parameters is indexed by L? Because you told me that L is the item, right?
I is the item. L is the is those items is those items who has updated during so a user, after the user is training in this round, some of the items in item embeddings will be updated, and this.
So my question is very simple now. So let's say you talk about the model parameters. Is the model parameter do the model parameters include the item embedding or not? I mean, the model, you say you saw a model, right? The model, does the model include this item embedding or not? Item embedding or user embedding, and then you also have the fully collected layer, right? According to your figure before.
Yeah.
Is the model include? So can you? I think you can go back to the when you define the mode this one, yeah. So what are here? Okay, let's say just this is the model. Let's say this is the model. What are the parameters of this model? For this model, what are the parameters?
User embedding, item embedding, and the non-embedding layers.
Oh, so the user parameter include this part, and everything here, right?
Yeah.
Oh, okay. And so here is the H, P, Q. Yeah. Yeah, not exactly. Okay. So then W So if you're using W to represent everything here, then they will include this user embedding and item embedding.
Yeah.
Okay, can you go to the algorithm that the last slide that we discussed there, and this one. So so what's the meaning for this command?
This is to find the item component for which the user has updated during this round. And
so they found the item set, which item has been updated, and then they just update their embedding weight.
This part is just update the item embeddings.
Yeah. But what is Q is the item embedding, right? Or Q is not is Q the item embedding parameters, or is not item? It looks like this one. So it looks like you have Q, you have W. I just not sure. So what's the difference between Q and W here?
Q is the difference between WK, the parameters learned, and the W0.
So Q is not the real, is not the embedding weight. I mean, it's not the embedding parameter, the parameter of the embedding layer.
Yeah, it's not.
So yeah. So I think this is confusing here. They use this embedding weight here, because the weight usually means the weight is the model parameter, the weights. But looks like this is more just like just like a coefficient.
Yeah.
Then they use it just trying to do a weighted average here.
Yeah.
Oh, okay. So then why this I belongs to, why the sum over S here? I saw this is round by round, right? Each round, oh no, not round by round. K. So K is the user, or K is the user, right?
Yeah, K is the user.
So for each user, you will find out for this user which item has been updated, and then you give them a weight.
Yeah.
Then why? So there's no time here, right? There's no time. You are not talking about time here. You are only talking about one single round or multiple rounds? I mean, in this algorithm here, you show here.
I think for this part, it's just one round.
So for one round, for each user, you find out a set of items. And then for each item, you will update in this weighted average.
Yeah.
Okay. Okay, yeah, let's just go ahead. Yeah, well, we'll see. I think about that.
Okay. In the next step, the user embeddings in the global model are directly replaced with the user embeddings from the local trained models. And then it will cluster users again based on their user embeddings. And a new user partition is formed using the newly obtained user embeddings. And finally, we need to update the user embeddings in which those users didn't partake in the training process. This is important because similar users will learn similar representations. So for this part, each user that didn't partake in the training process is updated using the user embeddings of all the participating users. And they have to share the same cluster.
When you say you are going to share with the other non-participation user, are you saying that they are going to, are they doing an averaging, or are they doing just a assignment?
What
they are
do
doing? So you mean exchange, right? You mean the share the changes. So when I share the changes, what are you going to do? Let me say for you, right? I have multiple participation user. You are not participating. Then we share our changes with you. So how are you going to use these changes?
So for this algorithm, this WK is the user embeddings of the users that didn't partake the training, and the W0 is the aggregate embeddings from the previous round. And this part, and I think this W0 is gathered from the previous training round, which is the and the previous training round is there are some participating users during the training process. And then they calculate the difference between these two. And then for each non-participating user in the cluster, they calculate the average difference between the average difference between WK and W0, and this one is a discount factor that decays as the learning progresses, and then added it to the user embeddings of the non-participating users. And finally, we get the updated parameters.
Okay. Okay. Yeah. I see.
So that's the whole algorithm of their proposed system. They evaluate their system using 4 publicly available real-world data set. And they adopt the leave one out evaluation protocol, which split data set into a training and a test set by randomly selecting one of the non-zero entries to be part of the test set, and using the remaining entries for the training set. And they recorded the average HR and NDCG on the top 10 recommendations. They calculate these two metrics for each test user and report the average score. And to make the comparison fail, they use the same hyperparameters for the Fed average and FedFast algorithm. First, they compare the recommendation performance for FedFast, Fed average, and to centralize the trained baselines. And the result shows that FedFast tends to reach a better recommendation quality than the Fed average. And as for the comparison to the centralized baseline, in some cases, FedFast tends to perform better. Then they observed across the data set that FedFast converges faster than the Fed average. And on average, FedFast reached the best performance at least 4 times faster than Fed average. Then they want to try to understand the relationship between the number of clusters and the recommendation quality. And what they found was the number of clusters chosen does not impact the recommendation quality, but it impacts the convergence speed. And finally, they did conduct an ablation study. Generally, it appears that the sampling method they proposed improves the performance, but the impact of their aggregation method is more significant. But both components are useful in improving recommendation quality and increasing convergence speed. And that's all.